A major focus area in nanoscience today is transforming semiconductors with chirality. Imparting chirality onto semiconductors expands their functionality by giving them sensitivity to and ability to generate circularly polarized light. In our work, we twisted previously achiral colloidal nanoclusters, close relatives of quantum dots, using meniscus-guided deposition techniques. Chiral objects are things that are not superimposable with their mirror image. Think about a screw, or a snail, or your own hand. Whereas achiral objects are objects that can be superimposed with their mirror image, like pencils or bottles. Controlling chiral light is important and has useful applications, such as in medicine, where it could non-invasively detect blood sugar levels. Researchers study chirality using circular dichroism, or CD, a spectroscopic technique that measures the difference in absorption of left and right circularly polarized light. Ignoring some nuance, if a sample has CD, it's chiral. If we consider an individual achiral nanocluster, it will have a characteristic band gap and absorption energy, but because it is achiral, it won't display any preferential absorption of left or right circularly polarized light. These are achiral nanoclusters, which means they don't natively have any CD or special chiral light twisting properties. But something amazing happens when you string these together into a helical assembly. The excited states, which are individually degenerate or equal in each individual particle, become shared across neighboring nanoclusters, leading to a splitting in the excited states. These new split excited states possess preferential excitability with circularly polarized light. The difference between the absorption from each of these states leads to a characteristic bisignate spectrum, the sign and magnitude of which depend on the geometry of the structure itself. In our work, we worked with a handful of nanocluster species. Each of these have a characteristic absorption band. We use cadmium sulfide, cadmium selenide, and cadmium telluride, each of which absorb different colors or energies. Notice that there's no circular dichroism, which you can see in the top panel, when they are in solution before we process these semiconductors. But then, we process these achiral semiconductors into films using controlled evaporation, like the well-known coffee ring drying effect, but with nanoclusters. After this, the films all possessed bisignate circular dichroism aligned with the absorption band, characteristic of the excited state splitting that we just described. To our surprise, though, the achiral particles formed large chiral domains, where the chiral structures across many, many millimeters in the film were all the same handedness, caused by forces during the drying. It's almost as if we're creating optical screws from nanoclusters. Think, to put a screw into something, you've got to turn the screwdriver the right way. The nanoclusters interact with light in a similar way based on the direction of their twist. Remarkably, the dissymmetry factor, which is the figure of merit for CD, indicates how strong a material interacts with chiral light, is huge from these structures. In fact, the values we measured are the largest ever reported for inorganic semiconductors, more than 1,000 times stronger than typical chiral materials. While there's some more R&D to do before we'll see chiral quantum dot TVs, the newfound control and tailorability over the chirality of semiconductors will enable their development into next-gen technologies relating to imaging, optical communications, and catalysis. Check out our paper to learn more about our discoveries.